You know how sometimes you just want the core knowledge, the real takeaways from something complex, without having to wade through mountains of information?
Mhm.
That's what we're doing today. We're diving deep into a topic absolutely vital to our planet.
Forests.
Yeah, forests. They're so much more than just trees, aren't they? They're a critical cog in Earth's climate system,
Mhm.
and a resource we depend on in countless ways.
Definitely.
And at the heart of understanding forests lies their biomass. Think of it as, well, the total weight of all the living stuff,
Yeah.
especially what you see above ground, the trunks, branches,
Right,
leaves.
the actual stuff of the forest.
Exactly. And knowing how much biomass forests hold globally is really key to understanding how much carbon they store. And crucially, how that's changing due to, deforestation, regrowth, or even degradation.
It's like taking the Earth's pulse in terms of carbon, almost.
That's a great way to put it, yeah. But here's the fascinating challenge, isn't it? How do you actually measure this colossal amount of biomass across the entire planet? I mean, imagine trying to weigh every tree in the Amazon or Siberia.
It's a monumental task. You just can't do it comprehensively from the ground.
Exactly. That's where some seriously clever technology steps in.
And we're going to explore a groundbreaking mission that's doing just that from space. It's designed to give us a truly global picture of forest biomass.
Okay.
Our aim today is really to unravel how this mission works and what incredibly valuable insights it will provide, but, without getting totally bogged down in the super technical jargon.
Getting the essential understanding, the aha moment.
Precisely. About this really ambitious endeavor.
Okay, so let's get right to it. What is the main thing this mission is trying to achieve? Like, what's its core purpose?
Right. The central goal is to create detailed maps showing the amount of above-ground biomass in forests worldwide.
Okay, mapping the biomass.
Yes. And this is critical because this biomass is essentially stored carbon. So by accurately mapping it, we get a much clearer understanding of the planet's carbon storage and, importantly, how it's being affected.
So it's about quantifying the role of forests in the global carbon cycle with like unprecedented accuracy.
That's it. It's not just taking pretty pictures of forests from space, although the data can look amazing. It's about something much more fundamental, our planet's carbon balance.
Right. Because changes in forest biomass directly impact the CO2 in the atmosphere.
Absolutely. I mean, if forests are cleared, that stored carbon gets released. If they grow, they absorb carbon. Better biomass data lets us track these changes with much greater precision.
Which must be incredibly useful for things like climate agreements.
Exactly. It supports international efforts to combat climate change. It provides a solid evidence base, for informed environmental policies.
That makes total sense.
Uh,
So, how does a satellite way up there actually weigh all these trees? What's the core tech?
Okay, so the key instrument is something called a P-band synthetic aperture radar, or SAR.
P-band SAR.
Okay, now the P-band part refers to the frequency of the radar signal, and this is really, really important. This particular frequency has, well, a unique ability to penetrate through the leafy canopy of forests.
Ah, so it can see past the leaves?
Exactly. It reaches the larger woody parts, the trunks, and the big branches, which is where most of the biomass is actually concentrated.
Unlike maybe other types of radar that just bounce off the top.
Precisely. Shorter radar frequencies tend to just bounce off the leaves in the upper canopy, giving you a less complete picture of the total biomass. The longer wavelength of P-band allows for that crucial deeper penetration.
Interesting.
And what's also fascinating is that P-band radar is more resilient to changes in the signal over time. Its phase stays more coherent, which is vital for getting consistent, accurate measurements as the satellite passes over the same areas again and again.
Okay, I'm starting to get a picture. So the satellite sends these P-band signals down, they interact with the forest, bounce back, carrying information about the woodiness, basically.
That's the core idea.
What happens after that? Is it just one quick scan?
No, the mission operates in carefully planned phases to gather different kinds of information. It starts with the commissioning phase, calibration, making sure everything's working perfectly.
Gendered stuff.
Right. Then comes a period of about 14 months where the satellite will make multiple passes over the same areas, but from slightly different angles.
Different angles. Why?
This technique is called tomography. It allows for a kind of 3D reconstruction of the forest structure.
Whoa, like creating a three-dimensional map of the forest, not just a flat image.
Exactly. Think of it like a medical CT scan, but, for forests. It gives us a vertical profile, showing how the biomass is distributed at different heights within the canopy.
That's incredible. And after that, the
Uh,
mission's longer than 14 months, right?
Well, yeah. After this tomographic phase, the mission will continue for the rest of its planned 5 years, using a technique called polarimetric interferometry.
Ah,
POLINSAR for short.
okay, sounds technical again. What's the key benefit there?
Well, both POLINSAR and the tomography data help scientists to um, isolate the signals coming specifically from the vegetation. They help minimize interference from the ground signal reflecting back.
Interference from the ground.
Yeah, sometimes the radar signal can bounce off the ground and then off a tree trunk before returning to the satellite. It's called double bounce scattering.
Ah, okay.
So by accounting for these effects using these techniques, we can get a much cleaner measurement of the biomass itself.
Right. So once they've managed to isolate the signal from just the trees, how do they actually translate that radar echo into a number, an estimate of biomass?
Good question. For dense tropical forests, where the signal scatters a lot within the canopy, scientists use quite sophisticated models to relate the characteristics of this volume scattering to the amount of biomass.
Models, okay.
And interestingly, research from aircraft campaigns flying P-band radar over tropical forests has shown a pretty strong link between the biomass and the radar signal reflected from around, say, 30 meters above the ground.
30 meters, that's specific.
Yeah, it seems that way. Something that tomography can specifically measure. It appears that in many of these forests, a significant chunk of the total biomass is concentrated in that upper canopy region around that height.
Fascinating. But forests aren't all the same, right? What about, say, northern forests?
Excellent point. It's crucial to remember that different types of forests have different structures. So, for example, in boreal forests, those northern ones, that ground interaction we mentioned, the double bounce scattering,
Yeah.
that actually carries important information about the biomass. So in those cases, the methods might not try to completely cancel out the ground signal. The estimation methods have to be tailored, really, to the specific characteristics of different forest types around the world.
So it's not a one-size-fits-all calculation.
Definitely not. Very adaptive.
That makes sense. So what kind of accuracy and geographic coverage are we expecting from these global biomass maps? How detailed will it be?
The goal is to achieve a resolution of about 200 meters for the biomass maps.
200 meters.
Yeah, so each pixel represents a 200 by 200 meter square. In terms of accuracy, the target is to be within 20% relative error or 10 tons per hectare absolute error for areas with lower biomass, under 50 tons per hectare.
And coverage everywhere.
The mission aims to provide global coverage of all the world's forested regions, yeah. Though, there might always be some minor limitations due to operational factors.
A 200-meter resolution map of forest biomass for the whole globe. That's still incredibly valuable, even if it's not tree by tree.
Absolutely. A huge leap forward.
And it's not just about biomass, right? I recall reading somewhere that this mission will also measure the height of forests.
Yes, that's another key objective. Both the POLINSAR and the tomography techniques can be used to estimate the height of the forest canopy.
How accurately?
The accuracy target here is aiming for better than 30% for trees taller than 10 meters. So this will give us regular global maps of forest height too.
Wow. So biomass and height. That must give a much richer picture of the forest structure, its health, maybe how it's developing.
It really does. Structure is so important. And beyond these core measurements, the mission also has the capability to detect significant disturbances to forests, things like large-scale clear-cutting.
How does it do that? I mean, I guess a clear cut would look quite different from a healthy forest in the radar data.
Indeed. The changes in the radar signals caused by such extensive deforestation are, well, quite pronounced. The mission aims to produce disturbance maps at a higher resolution too, around 50 meters.
Better resolution for change detection. Makes sense.
Yeah, the method involves basically analyzing the statistical characteristics of the radar data over time, looking for areas where substantial changes have occurred. That indicates potential forest loss.
That's a powerful tool for monitoring deforestation hotspots. But, with all this complex data coming down from space, how do scientists actually check it? How do they make sure the biomass and height estimates are accurate? Validation must be key.
Oh, validation is absolutely critical. You're right. And it's a huge challenge. This requires high-quality reference data collected on the ground.
Which must be tough in remote places.
Exactly, especially in, say, remote tropical forests. It's a significant logistical challenge. There are ongoing international efforts to expand these ground-based measurement networks, but it's hard work.
So what else can they use?
Well, data from airborne LiDAR instruments is also really important. LiDAR gives you very detailed 3D information about forest structure from aircraft. So that can be used to complement the ground measurements and help verify the satellite data over larger areas.
Sort of bridging the gap between the ground plots and the satellite pixel.
Kind of, yeah. It helps scale things up.
Okay, so let's pull back a bit. All this information, the global biomass maps, forest height, disturbance alerts, what's the really big picture impact? Why is this mission so fundamentally important for the planet?
Right. Here's where it gets truly significant.
Hmm?
Accurate global measurements of forest biomass are, well, absolutely vital for reducing the uncertainties in our estimates of the carbon cycle.
Uncertainties?
Yeah, huge uncertainties in how much carbon forests are absorbing from the atmosphere and how much is being released through deforestation and degradation. This mission's data directly improve the accuracy of our carbon cycle models.
And those models are what we use to understand climate change.
They're essential for understanding and predicting the impacts of climate change, yes. The data will also be used to refine complex Earth system models, leading to more reliable climate projections down the line.
So better predictions, better understanding.
Exactly. And it enables much better monitoring of forest dynamics, how forests are changing, and the rates at which carbon is actually moving through these crucial ecosystems. It's about getting a much clearer, much more reliable picture of a key piece of the global carbon puzzle.
It really sounds like it's filling some critical knowledge gaps.
Precisely. And, beyond its primary focus on carbon and climate, the mission has some really interesting secondary objectives too, stuff that leverages the unique capabilities of that P-band radar.
Oh, really? Like what?
Well, because of the long wavelength of P-band, it can actually penetrate several meters below the surface in very dry regions like deserts.
Penetrate the ground.
Yeah. This opens up the potential for mapping subsurface geological structures, maybe finding buried riverbeds or other features hidden beneath the sand.
That's amazing. Like having X-ray vision for the Earth in certain places.
It kind of is.
Mm-hmm.
Another objective is to generate a highly accurate map of the Earth's ground surface topography, a digital terrain model, or DTM.
Don't we have those already?
We do. But because the P-band radar largely sees through the forest canopy, this DTM will be free from the distortions caused by dense vegetation that affect some existing elevation maps. So a truer ground surface map.
Ah, very useful. Anything else?
Yes. The mission will also contribute to measuring the velocity, the speed of glaciers and ice sheets, and even provide insights into the properties of the ionosphere way up in the atmosphere by analyzing how it affects the radar signals passing through it.
That's a remarkable range of applications from one main instrument.
It really shows the power of the technology.
Now, obviously, this isn't the only satellite looking at Earth, or even at forests. How does this biomass mission fit into the broader landscape of Earth observation?
You're right, it is part of a larger ecosystem of observation. What's particularly exciting is how this mission complements these other efforts. Different satellites might have different strengths. Well, some might be better at detecting very subtle changes in forest structure using different sensors, maybe optical or shorter wavelength radar. Others might have a finer spatial resolution, but maybe can't penetrate dense canopies as well, or aren't as sensitive to higher biomass levels.
So they all offer different perspectives.
Exactly. By combining the data from multiple sources, including this mission, we can build a much more complete and detailed understanding of our planet's forests. No single mission can do it all.
So it's like different instruments in an orchestra, each playing a vital part.
That's a perfect analogy. This mission offers a unique and crucial piece, especially for providing these global measurements of biomass across a really wide range of forest types and biomass levels, which has been a major gap.
Right.
And of course, to truly understand what's happening in forest ecosystems, you need to integrate this biomass data, the amount of carbon stored, with other information, like estimates of net primary production, which is how much carbon the forests are actively taking in through photosynthesis.
So combining the stock of carbon with the flow.
Precisely. That gives you the full picture of carbon cycling. So ultimately, this mission is a vital component of a much broader global system for monitoring and understanding our planet's carbon balance.
Okay, so to really nail it down then, what's the core message here? What should we as listeners really take away about the significance of this mission?
I think the fundamental importance lies in its innovative ability to give us, for the first time really, a globally consistent picture of forest biomass distribution and how it's changing over time using this P-band radar.
A consistent global view.
Yes. And that information is absolutely essential for improving our understanding of the global carbon cycle, and critically, for effectively tackling the challenges of climate change and ensuring we can manage our planet's vital forest resources sustainably.
Okay, as we wrap up this deep dive, it's really clear that this mission offers a truly groundbreaking way to measure forest biomass and height from space. And like you said, this isn't just an academic exercise, it's about gathering critical data. We need to understand one of the most important parts of our planet's climate system, our forests.
Absolutely.
Having this kind of comprehensive global information just seems invaluable.
And that leads to a really important final thought, maybe for you listening. Think about how interconnected Earth systems truly are. Measurements like these, focused on something as seemingly specific as forest biomass, they have these far-reaching implications for our understanding of the entire planet and, well, its future.
Yeah.
So maybe ask yourself, what does having accurate global data on forests really mean for our ability to take effective action on climate change and to conserve these vital ecosystems for generations to come? It's a question that I think truly underscores the significance of this kind of endeavor.